Hello dear students, today we are going to discuss about RMS value of alternating current. In the previous section, you people have discussed about average value of alternating current. Average value or mean value of alternating current over one complete cycle. You might have got the expression I average is equal to 2Im divided by pi, which is 0.637 times that of Im. Which we can say the average value of alternating current for 1/2 cycle is 0.637 Im, means 0.637 times that of peak value of current, or 63.7 times that of the peak value of current, 63.7% of the peak value of current. If the peak value of current is, let us say, some 1 ampere, then the average value of that current, that alternating current for 1/2 cycle is 63.7% of that 1 ampere. That's the meaning. So, if you want to measure the current as the average value of current, then we can say I average is 2Im by pi, or 0.637 times that of Im. If you are given a magnitude of current, certain value of current, you can go on with this calculation. If peak value is known, you can calculate average value. If average value is known, you can calculate the peak value of alternating current. That is applicable for both alternating as well as direct currents. But here, we are going to speak about RMS value of alternating current. What is RMS value of alternating current? What is the necessity of speaking about RMS value of alternating current? If suppose a direct current circuit is there, which is connected with a battery, a component is connected with a battery. If you are asked to measure what is the amount of current flowing through the circuit, then with the help of an ammeter, you can easily determine the amount of current flowing through the circuit. Suppose, if you are asked to calculate an alternating current flowing through a particular circuit, what will you do? If you use the same ammeter, what will happen? For 1/2 cycle, the deflection will be in one direction. For the other half cycle, the deflection will be taking place in the opposite direction. In other words, if you use a galvanometer, then you can understand it very clearly. The pointer will be exactly at the zero position of the galvanometer. The values will be running over the positive as well as, means the right hand side as well as towards the left hand side. The values will be like this in the galvanometer. Let us say 0, 10, 20. This is 10, 20. Pointer will be like this. If you are passing a current through the galvanometer, as you know, galvanometer is used to detect the direction of flow of current. If it is a DC current, problem is simple. For AC current, what will you do? Deflection will be taking place for 1/2 cycle. As you know, alternating current is varying in magnitude as well as in direction. So what will happen? The deflection will be taking place in one direction for 1/2 cycle. For the other half cycle, the deflection will be taking place in the opposite direction. And that happens when the current flows very slowly. But what happens here? For 1 second, the number of repetitions of the sinusoidal wave is 50 cycles. Or otherwise I can say the frequency of the alternating current is 50 Hz. Household supply is 50 Hz. So what will happen within a second, within this duration, the deflection will be alternated for 50 times. So what will happen finally? The pointer will be reading only 0. So there will be no measurement studied in the galvanometer. So you cannot measure current using ordinary ammeter or a galvanometer. So what is the next step to study about or measure the amount of current flowing through an alternating current circuit? So we are introducing a term called RMS value of alternating current. Root means square value of alternating current. The RMS value of alternating current is otherwise called effective value of alternating current or otherwise virtual value of alternating current. So why they got the name? The RMS value of alternating current shows the same effect as that of a direct current flow through the circuit. This is an alternating current, but when you measure the alternating current in the form of RMS value of current, then the behavior of this RMS value of current shows the same behavior as that of a direct current. So it is an effect. So we used to call it as I effective or effective value of current. I virtual. Virtual value of current here means that virtually the alternating current virtually behaves as a direct current. Alternating current virtually behaves as a direct current. That's the meaning. So you can call it RMS value of alternating current, effective value of alternating current, or virtual value of current. So the time varying voltage or current can be measured using RMS value of alternating current, and this measure is applicable only for alternating current. It is not applicable for direct current. Whereas when you speak about average value of alternating current, it is applicable for both DC as well as AC. RMS value of alternating current is meant only for the measurement of alternating currents. So we can simply say here, on what basis the measurement has been done. We can say there are different ways. We can say only thing is that when electric current is passed through a heating element, whether it is DC or AC, doesn't matter. For the amount of current, heat produced will be H equals I square RT based on Joule's law of heating. So the direction of flow of current through a heating element is immaterial in this particular case. So whether it is a direct current or it is an alternating current, doesn't matter, the amount of heat produced will be the same if the magnitudes of currents are the same. So on the basis of Joule's law of heating only, we are going to, we will be calculating the RMS value of alternating current. If DC is producing this much amount of heat, then the same amount of heat will be produced by an alternating current. When it happens, then we can say the RMS value of this alternating current is equivalent to the DC value of the current flowing through the circuit. That's the meaning. Right. We shall go on with the RMS value of AC. How will you define RMS value of AC? The RMS value of alternating current is defined as the square root of the mean of the squares of all currents over one complete cycle. See the statement? RMS value of alternating current is defined as the square root of, then the mean of, for what the mean has been taken, the mean of the squares of currents, mean of the squares of currents over squares of all currents, that's the mean, squares of all currents over one complete cycle. So definition is very simple. RMS value of alternating current is defined as the square root of the mean of the squares of all currents. So you are taking the mean of the squares of all currents. So if an alternating current is taken, this current must be taken as squares. Then positive value will be taken as a square current. Negative value will also be taken in the positive quadrant as positive current. So square currents are taken. For all the square currents, you are taking the mean value, and that mean value must be taken a square root. Then if it is done for one complete cycle, then you will get the RMS value of alternating current. Idea is simple. So what you have to do, first alternating current is there. You take the square of the alternating current. Each and every for each and every time duration there will be a current resulting. You take the squares of all these current values, then the currents will become positive quantities. Square of the currents will become positive quantities. Then take the mean of the squares of all the currents. Take the mean of the squares of all the currents. Then after taking the mean, you take the square root for it. Take the square root for it. What will happen? You will be getting the RMS value of alternating current when it is taken for one complete cycle. As you know, how will you represent an alternating current? An alternating current is represented by I equals Im sin omega t, or I equals Im sin theta. Theta is equivalent to omega t, so either representation with the sin omega t or sin theta. I equals Im sin omega t or I equals Im sin theta is the representation for an alternating current. The alternating current is considered to be flowing through a circuit which is given by I equals Im sin omega t or I equals Im sin theta. Then you have to take the square of all the currents over one complete cycle. Then you will be taking the mean of the square of all the currents. If it is done, then you can calculate the value of RMS value of alternating current. Before doing that, you have to speak about this particular condition. If you are taking mean of the square of all the currents, how will you calculate the mean? you have to sum up all the currents and divide by that many number of current values. If there are n number of square currents, then you have to sum up all the n number of square currents and then you have to divide it by n, so that you will get the mean of the square of all currents. In order to do that, you are going to follow a simple procedure. The sum of the squares of all currents can be easily obtained by taking the area under the square currents over one complete cycle. Square of the currents over one complete cycle. What you are doing exactly? Instead of summing up and taking the mean, you are going to simply calculate the area under the curve of the squares of the currents over one complete cycle. Squares of the currents over one complete cycle. So I can show it with the waveform here. Let us say this is the waveform. This is theta. Theta is taken along x-axis. Current is taken along y-axis. Positive maximum is Im. Negative maximum is minus Im. I can show you the alternating current over here for one complete cycle, 0, pi, 2 pi. So for one complete cycle, this is the alternating current, which I can represent as I equals I naught sine or Im sine omega t. I am taking the square of these currents, all currents. I can divide it by different segments, different the elements. Then I can take the square of all the elements here, so that the square of the currents will be like this. The squared currents will be in the positive direction. So all the squared currents will be exactly in the positive direction. So I have taken the squares of the currents, and then if all the squared currents are taken, divided into so many number of small elements and then added up, then you will get the mean value of the current. Or in other words, I can say, if you take the area under the squared currents, if you take the area under the squared currents over one complete cycle, then you will get the mean of the squares of all currents. Then you will get the mean of the squares of all currents. So I have taken the square of the given current, sine wave. So that has become a positive curve. This is the positive curve. I have to sum up all the currents, square the currents. In order to do that, I am taking a small element, d theta. Small element of the squared current, d theta. The mid-ordinate of the squared current is I square. The mid-ordinate of the squared current is I square. And idea is very simple. Actually, this is the curve. In order to calculate the area under the curve, I am dividing the curve into so many number of small elements. If I take the elements over here, the curved portion of this particular element is supposed to be a flat one, because this is infinitesimally small element d theta. As this is very infinitesimally small, then we can say this portion of this consideration, this element will be very, very, very small. It is considered almost a flat curve. So that is how a mid-ordinate will be discussed in mathematics. So I square is the mid-ordinate of the element, what we have assumed in this particular case. So area of the small element can be given by I square d theta. I square d theta. Actually, if you need this area, this is a rectangular element, then length into breadth. Actually, this portion is simple d theta. This is also considered to be d theta. This slanting portion or sloped portion is almost flat. That is considered almost flat. That happens when you take infinitesimally small elements in mathematics. So when you speak about infinitesimally small elements, then this flat portion is considered flat. That is how we will be speaking about the mid-ordinate. When you take mid-ordinate, this lower half and this upper half, these portions will get cancelled out in the opposite sense when you speak about the curves in the opposite sense. So whenever you are taking the mean value of this kind of sinusoidal waves or cosine waves, you can go with the mid-ordinate, so that the addition of these currents or addition of these physical quantities will be very, very simple. So I square is the mid-ordinate of the small element d theta, what I have assumed. Then the area of the small element, the area of the small element, this element, is I square d theta. Area of the small element is I square d theta. Then what is the total area of this squared current wave? Squared current wave. That we must calculate. So, if you calculate the total area under the squared current wave, and you take the, if you take the area over one complete cycle, and if you divide it by the base element of, or the base of this one complete cycle, then you will get the RMS value of alternating current. Idea is simple. So, to calculate RMS value of alternating current, you must take the square root of the area of the square of all currents over one complete cycle divided by base width of one complete cycle. Base width of one complete cycle. To calculate the RMS value of alternating current, we are switching over to this particular formula, that it is the square root of the area of the square of all currents over complete cycle. The area of square of all currents will give you, for one complete cycle, will give you the mean value of the square of all the currents over one complete cycle, divided by base width of one complete cycle. Actually, this entire term will give you the mean value of the current over one complete cycle. So, the square root of the mean of the squares of all currents over one complete cycle will give you the RMS value of alternating current. So, total currents divided by total number of elements. That's the meaning. So, base width of one complete cycle encloses so many number of such small elements. What is the base width of the square of the current? See, 0 to pi, pi to 2 pi. So, total base width of the squared currents is 0 to 2 pi. Then area of the square of all currents over one complete cycle. This is a small element I have assumed. Then I can divide this entire squared curve into so many number of such small elements. If I sum up all the currents, then I will get the total value of square of all the currents. If I divide it with the base width, then I will get the RMS value of current. Instead of summing up, I am calculating the area under this curve, I square curve. So that I will get the total measure of the squared current, and divided by the base width, I will get the RMS value of current. The same statement in a different form, existing in a different form. Instead of doing this, RMS value of alternating current is defined as the square root of the sum of the squares of all currents over one complete cycle. I am taking the square root of, instead of taking sum, I am finding out the area. That will give you the sum of all currents. That's the meaning. Area of square of all currents over one complete cycle will give you the sum of the squared currents over one complete cycle. When divided by base width of one complete cycle, you are taking the mean of one particular cycle of the squared current. Then when you take root of that particular value, you will get the RMS value of alternating current. So RMS value of alternating current is very simple. IRMS equals square root of area of the square of all currents over one complete cycle divided by base width of one complete cycle. As I showed you in the diagram, base width of one complete cycle of the squared current wave is 0 to 2 pi. This is the base width. Then area of the square of all currents over one complete cycle, that is required. Area of the smaller element is I square d theta. I found the area of the smaller element. There are so many number of such small elements. So I have to calculate the total area under the squared current wave. So I can write total area under the squared current wave. Is integral 0 to 2 pi I square d theta. So what I am doing here, integration is nothing but the summation of all elements running from 0 to 2 pi. 0 to 2 pi is the base width. So I am adding up all the small elements which are falling between 0 to 2 pi. And if I divide it with the base width of the complete cycle 2 pi, I will get the RMS value of alternating current. So total area under the squared current wave is 0 to 2 pi, integral 0 to 2 pi I square d theta. As we saw, I is Im sin omega t, then the total area under the squared current wave can be given as integral 0 to 2 pi I square is substituted as Im sin omega t. So Im sin omega t the whole square into d theta. Instead of omega t, I am taking theta here. So Im sin theta the whole square into d theta. Im can be taken as Im square integral 0 to 2 pi sin square theta d theta. Sin square theta d theta. Im square can be taken out as this is a constant. Then integral of 0 to 2 pi sin square theta is 1 minus of cos 2 theta divided by 2 into d theta. So I can write, since sin square theta is taken, is equal to 1 minus of cos 2 theta divided by 2. 1 minus cos theta divided by 2. 2 is taken out. So Im square divided by 2 integral 0 to 2 pi. I am taking d theta inside. So I will have d theta minus of, or otherwise you can say 1 minus of cos 2 theta into d theta. 1 minus of cos 2 theta into d theta. Then this is equal to Im square divided by 2. Take d theta inside and integrate. So I am having two integrations here. 0 to 2 pi into d theta minus of integral 0 to 2 pi cos 2 theta d theta. Cos 2 theta d theta. I am integrating these two integrations. Im is common. Im square by 2 is common. So Im square by 2. Integral of d theta is theta between 0 to 2 pi minus of cos of 2 theta is sin 2 theta divided by 2 between 0 to 2 pi. So I have integrated these two integrations. So Im square divided by 2, theta is substituted with upper limit and lower limit, 2 pi minus of 0 minus of 1 by 2 into sin 2 theta. For theta I am substituting 2 pi, so I will get sin 4 pi minus of, for theta I am substituting 0, 2 into 0 is 0, so sin 0. 1 by 2 is taken as a common term. So Im square divided by 2 into 2 pi minus 0 is there, so I am leaving it, minus of sin 4 pi is 0, sin 0 is 0, so the entire term goes 0, since sin 4 pi equals sin 0 equals 0. So the value of the total area under the curve is Im square by 2 into 2 pi. This 2 gets cancelled out. We will get Im square pi. This is the total area under the curve over one complete cycle, which is Im square pi. To calculate RMS value of alternating current, IRMS is equal to the total area under the curve is Im square pi divided by base width of one complete cycle. As I told you already, base width of one complete cycle is 2 pi. Pi gets cancels out. Im square is there inside the root, so it will become Im when taken root. 2 is taken a root, so by root 2. So IRMS equals Im by root 2. What is the meaning for this? The RMS value of alternating current is 1 by root 2 times that of the peak value of the current or the maximum value of the alternating current. So RMS value of alternating current is 1 by root 2 times that of the peak value or the maximum value of the alternating current. So to calculate RMS value of alternating current, you have to take the square root of the mean of square of all currents over one complete cycle. In order to calculate the sum of the squares of all currents, I am not speaking about mean, I am speaking about the sum. Sum of the squares of all currents will be taken with the area by calculating the area of the square of all currents over one complete cycle. When it is divided with base width of one complete cycle, then you will get the mean value of all the squared currents over one complete cycle. When taken a root, you will get RMS value. When taken a root, you will get RMS value. So in order to calculate the area of square of all the currents over one complete cycle, we have to find out the area of a small element first in a squared current wave. I am assuming a small element d theta. The mid-ordinate is I square. The area of small element is given as I square d theta. Then the total area under the squared current wave can be calculated by taking integration between the limit 0 to 2 pi, because that is the width of the squared current wave over one cycle. So integral 0 to 2 pi I square d theta. I is the instantaneous value of current, which is Im sin theta. So for I am substituting Im sin theta square d theta. Im square sin square theta d theta. Im square is taken out. Sin square theta is 1 minus cos 2 theta by 2. So that is taken here. Equivalent is taken here and into d theta. Im square by 2. 2 is common, which is taken out. Integral 0 to 2 pi 1 minus cos 2 theta into d theta. I am splitting into two integrations. Integral of d theta, integral cos 2 theta d theta. Then Im square by 2 is the common term. For theta, I am substituting the limits, upper limit and lower limit. For theta here also, I am substituting upper limit and lower limit. Then this will give you 2 pi and this entire term goes 0. So I will get the total area under the squared total area of the square of all currents over one complete cycle as Im square pi. RMS value of alternating current is required. So this is equal to square root of the area of the squared currents over one complete cycle divided by base length of the complete cycle of squared current wave. Base length is 2 pi. So if you simplify it, you will get RMS value of alternating current. IRMS equals Im divided by root 2. This IRMS equals Im by root 2 can also be represented as 0.707 Im, or otherwise I can say RMS value of alternating current is 70.7% of the maximum value of current. RMS value of alternating current is 70.7% of the peak value of current. I can show you in the diagram here. So if Im is the peak value of current here, then RMS will be 70.7% of this peak value. So I can draw a dotted line here. This dotted or this full line represents IRMS. This IRMS is 70.7% of this peak value. This is the peak value. This is the peak value, of which this 70.7% is the RMS value. Its behavior is same as that of a steady current. So RMS value of alternating current is either given as Im by root 2 or 1 by root 2 times of peak value of current, or 70.7% of the peak value of current. This is how a diagram must be represented. For RMS voltage, I can write Vrms equals Vm divided by root 2. Same derivation. Instead of current, I have to use voltages. V equals Vm sin omega t. That is the initial representation for an instantaneous voltage, from which we can get the result over here. Vrms equals Vm by root 2. So, whether it is alternating current or alternating voltage, the RMS value of alternating current or RMS value of alternating voltage is 1 by root 2 times that of the maximum or peak value of the respective currents or voltages, or otherwise you can say it is 70.7% of the peak value of the alternating current. RMS value of alternating current can also be defined in this form. RMS value of alternating current is defined as the value of the steady current which when flowing through a given resistor for a given time, and it is a steady current, or otherwise I can say DC. Steady current which when flowing through a given resistor for a given time will generate the same amount of heat when an alternating current passes through the same resistor or flows through the same resistor for the same time. So RMS value of alternating current is defined as the value of the steady current which produces the same amount of heat through a given resistor for a given time as produced by an alternating current when passed through the same resistor for the same time. See the statement? I am passing an alternating current through a given resistor R for a time interval t. It produces certain amount of heat. If the same amount of heat is produced across the resistor R, same resistor R for the same time t, by a direct current, then this direct current and this alternating currents are equal. When you compare these two currents, you can calculate or you can obtain RMS value of alternating current. That is how it has to be defined. The RMS value of alternating current is defined as the value of the steady current. Is defined as value of the steady current. Means AC is getting the form of DC. So, is the value of the steady current which one flowing through a given resistor R for a time interval T will produce the same amount of heat as generated by an alternating current when passing through the same resistor for the same time. So, as generated by, if based on the idea what we discussed earlier, if a current wave is represented and it has n number of the currents divided in the base width, then I am taking the square of the current here, square of the current, this is I, this one is theta. If this is the square of the current, then IRMS can be calculated as IRMS is equal to sum of the squares, right? I1 square plus I2 square plus I3 square. I have divided it into n number of elements. So IN square divided by n. This will also give you the RMS value of alternating current. This is another form. When doing calculations, if the entire current wave is divided into n number of small elements, then the square currents have to be summed up. All the n number of elements have to be summed up, and then that must be divided by n. Then that is taking the root of the total currents. Then you will get the RMS value of alternating current. So, to calculate RMS value of alternating current, either you can sum up all the currents, squared currents, and divide it by base width or the number of elements, or otherwise you calculate the area under the squared currents and divide it by the base width of the complete cycle of the square wave, so that you will get the RMS value of alternating current. That is one form. Another definition is this one. Through this procedure also you can calculate the RMS value of alternating current, which will give you the same result. IRMS equals Im by root 2. Whatever the currents and the voltages we discuss in general, for household supply, let us say for household supply, the RMS value or the voltage rating will be always given as 230 volt, and the current rating will be always represented as 5 ampere. Frequency is always given as 50 hertz. What is the meaning for this? All these values indicated or represented are RMS values. 230 volt is the RMS value. 5 ampere is the RMS value, which means a 310 volt peak value of alternating current is given as the input to the household supply. Our household is getting a 310 peak volt, 310 volt peak volt as the household supply, whose RMS value is 230 volt. In the same way, if it is current, then you will be getting 7.70 times that of, or 7.07 ampere current as the peak value of current. What is the meaning for this? Current starts from 0, increases its or reaches its maximum as 7.07 ampere, then 0, then negative in the negative direction 7.07 ampere, then 0. This is how the current whose direction changes. This is the peak value of the alternating current, whose RMS value is, let us say, 5 ampere. Whose RMS value is 5 ampere. Whether a current or voltage is represented, then it simply indicates the RMS value of current or voltage. You should not confuse yourself. Whatever the household supplies, whether AC, a refrigerator, a washing machine, or any device, any electronic or electrical device, you just check out the power, the plug where it is connected, plug to which it is connected. There a metal plate will be fixed on the body of that gadget, and then you can read the values over there. It will be reading 230 volt, 5 ampere, 50 hertz. What is the meaning for this? This device or this gadget will work within a voltage of 230 volt or a current of 5 ampere. Means it is the RMS value of voltage and current. The peak value of this voltage and current can be easily calculated using the formula IRMS equals Im by root 2. Im equals root 2 times that of IRMS. So if you multiply it with root 2, 1.414. So if I say 5 ampere is the RMS value of alternating current, then 5 multiplied by 1.414 will give you the peak value of the alternating current flowing through the circuit. So this is how alternating current is measured. Example 4.18. Write down the equation for a sinusoidal voltage of frequency 50 Hz and its peak value or Vm is 20 volt. Draw the corresponding voltage versus time graph. They are asking you to calculate the voltage versus time graph. We can calculate the instantaneous value of voltage can be represented as V equals Vm sin omega t. So I can write this as V equals Vm is 20 volts, so 20 sin omega is 2 pi nu t or 2 pi ft. Frequency is 50 Hz, so 20 sin 2 pi into 50 t. So 20 sin 100 pi is 314 t. This is the representation for instantaneous value of voltage for the given data, and the waveform can be shown here. This is the time scale and this is the voltage scale, and I am drawing a waveform like this: 0, pi, 2 pi. The peak value of voltage is, let us say, 20 volts, so plus 20, and this one is minus 20, and the frequency value is 50 Hz. They have represented as 50 Hz, for which we can calculate the time period also. T equals 1 by f, so 1 by 50. 1 by 50 is 0.02 second or 20 millisecond. So the time for one complete cycle is 20 millisecond. This is 20 millisecond.